Whether don't remember whether Rondi mentioned the poster session is also a reception. We will have refreshments. That's Friday evening, tomorrow evening, 5 to 7. And we have an hour and a half break for lunch Friday and Saturday, so we thought you'd go out and check the local restaurants. But since we have only an hour here, we'll have a quick lunch upstairs. If you want to have a spot for the poster session and haven't already set one up, you can still do that. Can they still do that, Matt, by getting in touch with you? Yeah, so if there's somebody interested in having some kind of display, see Matt Miller. Okay, we have a pretty tight schedule, and we are hoping to have lots of interaction between the speakers and the audience. So I have demanded from all speakers that they hold their talk down to specified time. I doubt that anybody will obey that, but if they look threatened from the audience, they may get the point. So look tough out there and help me keep things in line. So without spending any more time, I want to start with the first session. I wanted Bob Megginson. I have asked to be the first presenter. Bob Megginson is Associate Dean of Arts and Sciences at the University of Michigan. He has been connected with MSRI for a long time. He was deputy director here for 2 years and essentially doing what, for the preceding 2 years, what I'm doing this year. So, Bob, please.
Thanks much, Hugo. And I'll try to be a role model and stay within my time because I know that these people are tough and they will drag me off kicking and screaming if I run over. First, I have to find my presentation here. I have a few PowerPoint slides. Okay. This version doesn't use F5. Got it. Okay, so I'm just going to take a few minutes maybe to do a little bit of stage setting by just saying why it is that MSRI is doing this conference. Now, as David and Hugo both mentioned, I've been very recently associated with MSRI as deputy director, so throughout you'll probably hear me lapsing into the we, okay, when I'm referring to MSRI. That will include MSRI. So I'll start right up front by saying, why is it that we want to do this conference? There's an answer which actually begs the question, which is, as you heard, because we have been involved in math circles for a long time. Since 1998 at least, when Zvezda Stankova was here as a postdoc, now at Mills College. It's certainly since then. Paul Zeitz was another one of the founders, and Hugo was a founder of Berkeley Math Circles, Bay Area Mathematical Olympiad, when he was here during his first term as deputy director. So the program has been going since then. It's been administered by MSRI ever since. So in one sense, the reason we're doing this is because we have been doing stuff with math circles and mathematical Olympiads for a long time. But again, that begs the question because it doesn't say why we got involved in it in the first place. So let me say a few words about that. I want to go back to one thing first of all, I think you would all expect me to say, is we need to develop mathematical talent. We know that there are pipeline issues involved right now with getting more students involved in mathematics. It's particularly important for MSRI because our mission, both parts of our mission, the development of new mathematical talent and having the developed mathematical talent to conduct and participate in the programs depend very, very closely on having that talent coming up through the pipeline. Students who really love mathematics, who have an aptitude for it, need to be encouraged to stay in mathematics so they can become the postdocs maybe 10 or 11 years after they go through a wonderful math circles, math Olympiad experience that said to them, yes, this is what I really want to do. We need to have those students. We need to have them coming back a few years after that to be the leaders in the sessions. If they're not there, it's not going to happen. All of you, and in some sense I'm preaching to the choir, all of you know that there are issues here. I'm going to show you a few numbers. You probably have a set of your own. They all pretty well tell the same story. Okay? Does the U.S. need to foster and encourage mathematical talent? Well, let's take a look at the bachelor's degrees awarded in mathematics in recent times. Let's say over the last 40 years. In 1966, about 20,000. That was about 4%, a little bit less than 4% of all bachelor's degrees awarded in this country went in mathematics. 1970 was a banner year. It had gone up to 27,000, almost 20, well, between 27 and 28,000. Because the baby boomers were coming through there, of course, the total percentage of all degrees had dropped just a little bit, but really, things still look pretty good. Where is it now? 2001, look what we're down to. We're down to 11,000, and that's less than 1% of the bachelor's degrees that are being given in all fields in this country. So things aren't looking too good there. At least one bright thing. By the way, I'll give you the source for this. I'm just going to flash it up quickly. If anybody that wants that, I can certainly give you the reference. At least we know that along the way we're certainly picking up a lot more women in mathematics, right? Well, let's look. 1966, 6,700 roughly, about a third of all mathematics bachelors being awarded in this country. 1970, 10,000. And in 2001, it had gone up to, dropped down to about half of what it was. We're seeing more women in our mathematics, our undergraduate mathematics classes, because there's been such a plummet of men that they're more visible out there. There's about half, now where you had about a third of those large numbers of undergraduate mathematics courses be women. Now with the smaller number and the smaller class sizes perhaps, sure, you're seeing half of the people in those classes be women because the number of men has dropped so drastically. We're not doing as well as we were doing in 1966, though, if you look at the absolute numbers. Just one quick slide. The conventional wisdom is that many of those are disappearing in other science, engineering, mathematics tracks. That certainly is true. If you take a look at the NSF numbers from the same source, the absolute numbers are going up somewhat. If you look at the classically mathematics-based fields, science fields, while the numbers are going up, the percent of all bachelor's degrees that are represented by all of those numbers are still falling. Now, what I did to get these numbers was to take the NSF numbers for all sciences, and I backed out the numbers for the sciences that are not classically mathematics based. So you can see what I did there, and you can quarrel with that computation if you want to. I think if you do your own, doing different numbers, so it's going to tell you the same story. Even in mathematics based discipline, the percentage of students choosing those options is going down. Well, those are bachelor's degrees, but maybe we're sending them off to college. Wanting to do mathematics, and they're losing their interest in college. That doesn't seem to be supported by the statistics either. This is a different set of numbers, okay, and it tells a different story. But if you take a look at what I've got up here, it's telling you that the fraction of U.S. college freshmen who are already inclined to want to do mathematics, they want to major in some classically mathematics-based science, engineering, math field, who actually specifically intend mathematics or statistics. The numbers I had did not break those things out. But our logical pool, how many of those students are really wanting specifically mathematics and statistics? That's dropped by quite a bit since 1975. We're losing students from our own logical base. We need to be encouraging them. Okay, so let's just quickly go on to some questions we would like to explore in this conference. Okay, we know that we need to be developing exceptional talent to help with these numbers. So where does it come from? How do we identify it? What are some of the different models used for math circles? How can we exchange some of that information and maybe enhance all of these models? Can they be improved by discussing maybe some of the drawbacks? And finally, are the models addressing the needs of students from diverse backgrounds? I think we really definitely need to look at that, because if you look at some other numbers that are going to be discussed later today, you'll see that maybe that's a place where mathematics is not doing too good a job. But ultimately, I do have to say, if you want to ask why it is that we do this, this is the best answer right here. If you go to one of the award ceremonies and you see the students, Zvezda actually took this picture earlier this year.
I could not have. I'm on the picture.
Okay, I'll put it this way. Yes, you pointed out the self-referential problem here. It came from your camera. I know that it came from your camera. Okay, so you still get the credit for it. Okay, despite the obvious discrepancy there. I was hoping somebody would notice that. But seriously, if you go to one of these award ceremonies and you see the smiles on the kids' faces who have had a chance to do something that they love, to work with other students who love the same thing, to have learned through a year's or more worth of math circles and Olympiad activities that it's okay to like math. It's something that it's okay to be good at. There are others who are interesting people who are good at it. It's that kind of fostering of talent, I think, that really charges us and makes us want to see this model spread further, and the reason that MSRI wants to be very much involved in that spread. Thank you.
Thanks, Bob. Really, that kind of experience of seeing the kids enjoy it, you see at all of the sessions of the math circles as well, and as you know, in all the competitions that we run. I forgot to mention something extremely important, that this conference is supported by a generous donation from the Akamai Foundation and also from a grant from the National Science Foundation. The pleasure of introducing the next speaker reminded me that I had forgotten that. The next speaker is Mark Saul of the National Science Foundation.
Now, see, they say that I have a PowerPoint. Let's see. That's fine. How do I do it? Slideshow, right? Okay. All right. As they said, Mark Saul, Program Director, Elementary, Secondary, and Formal Education, National Science Foundation. You can tell I'm from Washington because I'm one of the few people in the room wearing a tie. The name of the talk is Embroidery or Fabric, and you'll see that later. I told people I was just in India, and you can see from that what. Anyway, my day job is Sydney University of New York Research Foundation. Many of you know me from being leading the New York City Interscholastic Math League, the American Regions Math League, the Research Science Institute at MIT. But in real life, I am a, at this point, retired high school teacher. That's where I did the majority of my work. Bronxville High School, Bronx High School of Science, and several other places around the New York City area. And I have the battle scars to prove it. So my talk is very much from the classroom and what you can learn from mathematical circles and how it relates to things in the classroom. I will get from that to what you're all looking for, which is money. And the point is that they're related. Here's a little problem. I dare to do this in 3 or 4 minutes because of the audience I'm with. But most people, some of you will have seen this already. Many of you can do about 20 more like this and even better. But humor me. Okay. You take the set A, B, you form all the subsets, and you put them in a sequence so that each subset has either one new element added or one old element deleted, and you can say this to a 10-year-old. And you give them some examples, and pretty soon they get the idea. They make a little map, and you ask them how many ways can it be done. Well, it can be done in 8 ways. You can start at any vertex, and you can go in either direction. And then you ask, what's the next question? Well, if they're a little older, if they're not older, you just give them the next question. The next question is 3 subsets, three elements. There are 8 subsets. You might want them to count them yourself and so on, and do the same thing. And they fump around, and there's an example. There are some examples, and then you ask how many ways, and they get the idea that it's possible, and there are a lot of ways. And then you ask them to make a map, or get that out of them, like you did with the squares. And that's a tough point, because they start making the maps, and it's all over their page. This is the best map, in case you didn't see it already, didn't figure it out already. But it's a hard point in the teaching because they're thinking in 2 dimensions, and you have to look at their 2-dimension diagram and visualize it in 3 dimensions and pick the one that's closest to a cube, have them put it up, and then somebody will say, oh, it's a cube. But that's a hard thing to do, but you can do it. And the job is counting it. Okay, where does this go? Well, then you introduce characteristic function, and you see what I mean? I can't do this quickly with most audiences. And then from that, it becomes the standard unit cube on 3 dimensions, which people tell me I draw backwards, but I'm too old to change. And then you talk about binary counting, and I think you can see why. Binary counting, this is 0 to 7. But because what this is headed to is binary gray code. Binary counting, and you have to flip more than 1 bit going from, say, 1 to 2 or from 4 to 5. But if you code them differently, and this is a problem they run into, you run into in computers, you can do it sequencing, put them in a sequence, we only do 1 at a time. And that's what we're doing. So it leads to, the point is, it starts with almost nothing, with something that a kid can do who's 9 or 10 years old, and I have the experience to prove it. And it leads to significant issue in computer science. This is something people study. And it leads even further. You can see it's Hamiltonian circuits. It's the Tower of Hanoi is the connection. There's a connection to the Chinese rings. Oh, I brought a copy of the Chinese rings if you haven't seen it, but I left it in the room I'm staying in. Space filling curves, campanology, and probably lots of bell ringing, which is, they keep explaining it to me and I keep being bored, so I don't know anything more about it than how to spell it. I think I know how to spell it. But there's lots of interesting stuff you can dig into, and you can go for miles on this kind of thing. The issue being, look what they've learned from this about subsets, about counting, about geometry and symmetry, about the notion of dimension, because of course the next issue is, what if you have A, B, C, D, and then they go gaga over that, and then you say, well, A, B, C, D, E, and after you convince them that they can actually handle 4 dimensions, to go to 5 dimensions is, anyway, they're very impressed. Characteristic functions, coordinates, graph theory, all this stuff. And I'm not sure what else. Maybe somebody here could tell me more that you can do here. I don't think this is by any means exhausted. And the point is this an embroidery on the fabric of mathematics? Or is this actually the fabric of mathematics? And to me, that's the question when you do things in math circles and informal math and that kind of stuff. And the answer for me is the answer to a lot of these questions. It depends on how it's done. A lot of people look, for example, at curriculum, and they say, is this a good curriculum, this is a bad curriculum? And they're looking at the textbook. And the problem is that curriculum has no agency of its own. It has to be enacted by a teacher in a real-life classroom. And depending on how that happens, it's going to come out totally different. So it's, to me, only a very blindered thing to do, a very narrow thing to do, to look only at the written curriculum. And it's also a very narrow thing to do, to ask this question of a problem like that. My point is that you can tease things out that are much wider than just tricks you can do with your mind, if you know mathematics or if you like mathematics. What does this have to do with this conference, especially since a lot of you know this stuff already? Well, the issue is NSF and funding. National Science Foundation is charged with overseeing education in STEM fields for the entire nation. A mathematical circle activity is very, very narrow and small, and you're working with a tiny identified population. So how do you relate the two? Well, that's what I'm trying to say, that you can think globally, act locally. Did I say that right? Yeah, okay. And think about how the things you do in a mathematical circle can impact a wider effort. And then you can approach NSF for funding. And I think this is valid. I don't think this is a trick that you have to get milking the government for money in a certain way. I think this is why we do mathematical circles. And Bob mentioned some of the reasons why this kind of work has a national impact. I just want to explore another dimension to this, which is very au courant in NSF, which is the notion of research. Research in the sense of accrual of knowledge. You just don't work with 10 kids in a room and don't just do good work, but we learn something from having worked with those kids. So what are some of the things you could learn? Well, obviously you could work on problem sets, but not just problem sets because they're nifty problems. Problem sets because they teach something, they lead somewhere, or they lead to each other. Problem sets so maybe they articulate with regular curriculum. Problem sets so that they, if you can find a way of arguing this cogently, they engage kids who would not otherwise be engaged. And what I'm spouting here is very much including but not limited to. I think that the field is much wiser than any one program officer at NSF, and I leave it to you to develop it, but I'm just giving you some ideas. There's the tradition of elementary mathematics from an advanced standpoint, Felix Klein, those kinds of discussions, which is sometimes very useful to have with kids, or very useful to kind of debrief yourself after you've worked with students. What is it that they've learned from my own point of view as a mathematician? I don't think we have nearly enough of that in literature. There's the whole notion of heuristics in the tradition of George Polya. You might want to team with an educational researcher and look at the process of kids learning about problem solving. Don't waste that effort with it. With just 10 kids are doing problem solving. Get somebody in who is skilled and who can help you talk about how they learn this. Or even on another level, how do we observe this? What are the tools we use in analyzing this? I'm not sure that those are well developed at all, especially when we have high ability kids. There's not nearly enough in that. And what high ability means is itself a question. I would argue with any kid, we don't have enough of that. Maybe you want to work with teachers. Look at how teachers can use the kind of things that you work at in a mathematical circle. How it could stretch their own content knowledge, not just which is a big national problem. How you'd use them to teach problem solving, to integrate the problem solving into the classroom. How they can make their own contributions to the field. What do teachers know that you and I might not know? I say that a little disingenuously because, of course, I am a teacher, as I said at the beginning. And the reason I'm giving this talk is because this is very much from my own experience. I learned about teaching mathematics from teaching with math teams and math circles. And I got into, reform mathematics, developing curricula and so on through that process. And it very much was a process of learning how to take those techniques and use them with regular kids and even with remedial kids. I've used this problem about the subsets in the grade code with remedial kids. They don't get as far, they don't get as quickly, but the kind of thinking they do is very much the same. All right, if you want to, I'm finishing, Hugo. This is the money part, so I think they'll listen. My division, elementary, secondary, and formal education, has 3 big areas: instructional materials development, IMD, teacher professional continuum, TPC, and informal science education, ISE. This is all on the web, so I didn't make a slide about this. But what you have to do is, if you have an idea such as I had, or some even better idea, you have to find a way to fit it into the NSF agenda, which is, it might be a tight fit, but it is possible. Right now, there's nothing mentioning high ability kids or pipeline in any of these. There's a lot under discussion, so stay tuned. The reason I told you this is because I don't know when it's going to happen or how quickly, and I want you to be able to access some of these sources of funding. IMD, instructional materials, is curriculum, so it's more written stuff for students. TPC is development of teachers. So it's written stuff for teachers or activities for teachers. ISE, informal science education, is community activity. Museums, you know them because of their IMAX, because they work with the Exploratorium, those kinds of things. If you can see a connection there, it apply to them. And there's one more, and then I'll really finish, and that is, this is something which is hard to find, and I teased it out. This solicitation, which is enlarged, I can't pronounce this. They had this was originally Vigor, if you remember Vigor. And the only virtue, it seems to me, of all these acronyms is that you can pronounce them, and they've lost that virtue. So I don't know what. So it's enlarging the mathematical science workforce is the general umbrella, and inside mentoring through critical transition points. And I think Bob gave a very cogent explanation of how this is a critical transition point. They have language in their solicitation which talks about working with high ability high school kids quite specifically. So you might want to talk to John Conway or Liz Tellis. John Conway's Division of Mathematical Sciences, and Liz Tellis is Division of Undergraduate Education, who are the point people on that. And thank you for your kind attention.
I just want to take a minute to thank Mark for introducing several of the important threads of this conference. One is, what is it that we do in math circles and competitions? The other is, in what sense is it, I like that, the fabric of mathematics? And finally, and I hope we get to this on Saturday, is how does this relate to the broader picture of mathematics instruction and developing the workforce in the broader sense? So thanks a lot, Mark. Now, I haven't seen him this morning. I hope he's here. Is Dmitri Fomin here? Ah, you will be our next speaker. It's a pleasure to introduce Dmitri, who has long been associated with mathematics circles. There's no way here.
Oh, that's amazing. And the price is my turn.
There you go.
Thank you, Hugo. Thanks. I don't have, I'm sorry. I don't have a PowerPoint presentation, but I still will be using the computer as kind of a support device for my messy notes that I've done yesterday, mostly fine-tuned them on the plane flying from Boston here. And Bob Megginson just mentioned 20 minutes ago the models of math circles. I don't remember the exact phrase, but that's, I want to talk about something more general, and this very general picture, very with a broad brush. Models of extracurricular mathematical education, as I've observed them by my experience with them, mostly, but not all of it, in former Soviet Union and Russia, starting 20 years ago. So, okay, let's start. I will. Yes, but I can use one of those, right? Probably the left one would be the best. I don't know. I promise not to use them very often, but just for the general diagrams.
They're the experts when we need them. There is a little.
Is that thing at the foot?
No. There's a little handle that goes up
Basically,
there.
you just have to pull, but
Let's
to get
both
the
try.
place to pull.
No, you gotta unlock them from the from those handles or whatever. Oh, wonderful, wonderful, thank you. So, you probably can just disconnect this thing entirely, or oh, beautiful, thank you. Am I talking too loud, or is that okay? Okay. Just louder? Okay, thank you. I will try. So the model number one, let's call it Metropolis Math Circle. And this model is especially close to my heart, because this model is basically right now still implemented in my native city of St. Petersburg. What is the model? Basically, what do we have here? We have a large metropolis, like, with millions of people of population, 5 million, 2 million, whatever, and strong traditions of out-of-school scientific education. For example, in St. Petersburg, it began some point in 1960s when a lot of local enthusiasts, professors, teachers of math, graduate students, they've just realized that they needed to educate school kids differently outside regular elementary, high school, whatever, middle school curriculum, because mathematics has moved on, you know. It needed to be done differently. So they also had to engage kids, you know, students, teach them some stuff different from the same boring old stuff, you know, they were taught. Very repetitively taught in public schools at the time. So they began the creation of kind of a network of mathematical circles in the city, which eventually gelled into something like from 30 to 50 mathematical circles all over the city, concentrated mostly around two centers. One was more or less official one. I won't bore you with the names. And the other one was called something like Youth School of Mathematics, but basically it was a network of math circles. Currently it's operating on a smaller scale. I just want to emphasize the result of this process, because I doubt that it's extremely interesting for you to know what exactly is going on right now in city of St. Petersburg, or maybe somebody wants to know, but they can come to me later on and inquire. The result is this. Basically, for the last 30 years in that city, or in some other cities, that system made sure that no, let's call it, no child was left behind, so to speak. And what it means is this: if a school kid or his parents, her parents, feel that she has interest in mathematics or in physics, something like that, attracted somehow to it, then she knows, her parents know, her teachers know that the system is there. It exists. They know where to go. They know that there are math circles doing this thing. They know that there is very clearly organized and well-known system of Olympiads, well-structured, etc., etc. Okay, so this is the first model of whatever ECM education, or as Mark calls it, informal mathematical education, but I don't really like the term informal, so I'll stick with extracurricular math here. Okay, second model, I will call it metropolis schools, seminars, something like this. It's basically what is done right now and for the last 20, 30 years in Moscow. A lot of enthusiasts again, mostly students of the university, graduate students, postdocs, recent graduates of the universities. They act as teachers in some of the schools in Moscow, let's say 5, 7 to 10 of them. They combine both regular teaching and extracurricular math. This system has some advantages, definitely, because when you are a teacher in the school, you know, you communicate with the kids all the time, not just once a week for a couple of hours. You teach them math, regular math, and then you go and enhance that, supplement that with the all the extracurricular stuff you want to, and you know what material you base this thing on. But the same thing is the downside. It's the other side of the coin. Since this is the public school, you have to teach them regular math. You have to spend your energy on that. And also, you have to account for the fact that the majority of your kids in school, they are not ready for advanced math, which I'm still learning how to deal with this thing. I mean the microphone. So this is what's good and what's bad with this system. Models 3 and 4, I call them, let's call them city, university, and city, teacher. Those are basically models for smaller cities, like mid-sized cities, small cities. And the names are more or less self-explanatory. That basically means whoever's in charge of conducting the extracurricular math education in this particular small town and in this mid-sized city, in some kind of network, who creates it. So the main problem usually in this case is the insufficiency of the local pool of educators. You know, people willing to spend time teaching kids extracurricular math. I again can name a few, say, Russian towns here, but I doubt that would be of great interest, you know, who's following which model. I wanted also to say that success of these two models and models 1 and 2, regardless whatever system is in place, is rooted very much in the fact that this network is very firmly linked to the local universities and colleges. It's absolutely necessary for it to function properly. The teachers come from that pool, and they inevitably and quite properly guide the kids to that system, you know, teach them not to settle for less, for mediocre colleges, mediocre mathematical programs, etc., etc. Okay? These two models, 3 and 4, they will inevitably fail unless they are supported by some larger network. Other cities, in the same region, in the same state, contacts, exchanging ideas, coming to see what the other people are doing, conducting math camps, etc., like that. Or there must be some centralized education center that supports this. And here I come to the last model, number 5, which is also very dear to my heart. Let's call it net teacher. And it's basically, it's known to you by the other name, and not only to you, but by the name of correspondence school. Okay, because that's how it was initially done 30, 40 years ago in various countries, in Russia too. At the same time, approximately, where all those efforts, say, in Soviet Union, came to pass, sometimes in the beginning of the 60s. It's no coincidence that the correspondence school was created at the same time as well. And I know that there were attempts at creating some American analogs here, and some of them have failed, not all of them. And in my opinion, this could be the most important model right now at this stage in the ECM education here. We're not talking, of course, about some huge central entity covering the entire country with its, holding it in its clutches and, telling everybody what to do. There's no way, even they couldn't create that even in the former Soviet Union. That was some centralized state. But, on state levels, definitely that's something that I think is very important. Okay. Okay, I need to skip this. Sorry. Yeah, and here I come to some to the last part. Some notes about the relevancy of all this for the United States, hopefully, and some issues, concerning possible implementation of this thing here. once again, I want to emphasize that the systems will only work if they are known to exist. Everybody must know about them. So this is my first main point here in this part of the talk, making the particular local model, state model, whatever's in place there, known, popularized, so everybody who even remotely is interested in his or her kid getting some good mathematical extracurricular education, participating in Olympiads, contests, whatever, they must already know where to go. The teachers must know, the local colleges must know, even the parents should know, if they are, if they want to do that. So this is the first point, making the local model of ECM education extremely well known. Secondly, it's the attraction and motivation of the kids, because I mean, even if they know but they don't like it or they don't care for what mathematics is, what's taught in school, they need to be somehow attracted to this. And here I might be sounding a little controversial, but I think that extracurricular mathematics need to be made a little more, I don't know the right word to use here. I wanted to say sexy, but that sounds sporty maybe. Well, Olympiads and contests are in place already, but I don't think they quite play this role to the hilt. That must be done better, I think. I wanted to say more, but I'm already out of time. Well, we all know that kids are more than willing now to abandon their skills in pure sciences, even if they have them. If they're interested in math or in science, they would rather go quite often into medicine or law or humanitarian sciencey things, or into some intricate money juggling. So this is a huge problem for scientific community, and it has no easy solution. I just wanted to mention that. And the last point, third point, is that ECM education, I think, should be made on one hand simpler, even simpler than it is now, more popularized, but with a strong main message. I mean, I'm against myself feeding 10th graders or 15, 16-year-old kids brain teasers, because that's, I mean, you can give it to them when they are 10-year-olds, 11, 5th grade, 6th grade, just to get them interested. But to do that for 5 years straight without, and that's what I unfortunately see in some attempts to teach extracurricular math. That's bad. I mean, here's what I mean. Make it simpler. Make it very simple. I don't want to say dumb it down or whatever, but there must be one single main message. And that message is we need to promote the idea of real mathematical proof, real rigorous logic, even if the proof is extremely simple. It should not be problems in the vein of, draw 3 lines that pass through all these 9 points or something, and then the next day you give something like this. And it's mathematics too, but you cannot do that for too long, because that will drive kids away. I mean, of course, we all would rather teach school kids Galois theory and then dazzle them with what can and cannot be constructed using straight edge and compasses, and wow, that's really attractive to us as educators, I know, but we cannot do that usually. I mean, once in a while, maybe once in 10 years, but that's it. That's the 3 points, and I'm sorry I definitely ran out of my time, but thank you.
So a question before us is, can we build in the United States, or I should say in North America, a system which is maybe based on a few crucial centers like this, but really at this level and supported through the internet by interaction. So that topic will come up again. I now want to pass the baton to Alexander Soifer, who has long been connected with competitions. You've run a competition in Colorado Springs for over 20 years,
Yeah.
maybe even longer. So here's Alex.
Can we get it overhead?
The overhead. Okay, that'll take a minute. Bear with us, folks. It's a little unstable, but I hope
Okay. Hi, my name is Alexander Soifer, and I was once born in Moscow, and to a family of a painter and an actress whose philosophy of life in the Soviet Union was, for talented and honest people, there are arts and sciences, and leave politics to those who lack one or the other. And so that's how I grew up. And at the age of 6, musical pitch suddenly occurred in me, and I was sent to music school to just write piano music and play. And by 15, I graduated from this music school, and I was expected to continue that the rest of my life. As you know, I haven't. And let me spend a minute explaining why I haven't. In 1960, when I was 6th grader, my math teacher told me, would you like to spend a Sunday going to some Moscow math Olympiad? I had no idea what it was. I was a straight A student because it was easier to do than to explain to my mother an on A. That would have taken longer, so. But mathematics wasn't my favorite at all, you know. It was pretty boring to have formula for everything. For linear equation, a formula. For quadratic, a formula. But this math Olympiad that I encountered when I was 12 years old was fascinating. The problems were quite different. They didn't require any particular knowledge. They required something else. It was fun. And so I won something as a 6th grader, 7th, 8th, and then the moment of truth came, and I told my parents that I want to be that thing, a mathematician. And there was a lot of battles, and I am a mathematician. I probably chose mathematics because it's beautiful and surprising. No, I think I chose mathematics because it was easy compared to music, which was very hard work.
to tell you the truth. But I later learned that mathematics can be hard work too. It all depends. Okay, and so as an 8th grader, I got into a mathematical circle that was led by Nikolai Nikolaevich Konstantinov, whom some of you may know as a creator of International Tournament of Towns. It was Saturday afternoons for, you know, kids to keep them off the street and maybe interested in math. And no, we were all interested when we came to this mathematical circle. And for summer, after 8th grade, Konstantinov gave us a few problems so that we can do something in the summer. And I came after that summer very embarrassed. I told him that this geometrical problem took me a whole month to solve. And he was more happy not that I solved it, but that I stayed with it for a month. And that's how it all started. Okay, roll forward. I gave up my affiliation with the Soviet Union in '78, promptly deposited my citizenship, and I came as a refugee to the Plymouth Rock, that then was called Boston, spent the winter, and then moved west in a covered wagon with U-Haul on it, and I've been ever since that time in Colorado, the University of Colorado. Only last 2 academic years I spent at Princeton University doing research, and I'm back in Colorado now. So now that you know about me a little bit, let me talk about what I'm doing. In 1984, I started Colorado Mathematical Olympiad, and the next April 22nd, we will offer the 22nd annual Colorado statewide Mathematical Olympiad for middle and high school students. It's very much in style of Russian Olympiads, except I can't afford to create it grade by grade, and so problems are the same for whoever comes. 6th grade through 12, 5 problems, 4 hours, and later Bamo started very similar reglement. Let me tell you that it's not bad, as some may think, that problems are the same for everyone. I think it's good, because it totally doesn't allow us to use any topic. We can't allow seniors to have advantage over freshmen. So there is no topic involved, and I like that a lot. We have to come up with problems that use something other than topic. And as an example, in the year 2000, the first prize in the state of Colorado went to an 8th grader, middle school student, who in addition was an autistic kid. So, and came from a poor family, without a computer, normal school, nothing magnet about it. Yes, I need to show you a couple of slides, and then I'll talk about publications. What is it I'm trying to pursue? Well, first of all, I'm trying to show that mathematics is one of human endeavors that studies beauty, like this. That is a Fang tribe of Gabon, guardian reliquary statue. Well, mathematics simply uses different means. And here is how the Olympiad looks. For those of you who are interested, I have a few copies of 2003, and this is 2004. As you can see, we're trying to stay with the current events. Middle school students especially love it when it's not problem 1, 2, 3, 4, 5, but there is a story. And the first story was Homeland Security. And you know what? They may have done as well as Tom Ridge, which was easy. The problem 1 is the easiest, and then it goes harder, harder. And as you can see, it talks about coastline. And imagine, 5 days after the Olympiad, Mr. John Kerry talked about coastline. So we were 5 days ahead of the trend. Okay. Oops. The problem 3, as you can see, is called Crawford Cowboy Had a Farm. E-O. And that problem was clearly inspired by a Crawford farmer. Actually, it was August CIA FBI briefing that Osama bin Laden is planning something, and CIA people were here, but I noticed that if you symmetrically reflect the president, then you will see these cowboys lean like a cowboy from B movie, and I like that. And so, problem 5 is the hardest. Oops, where is it? Yeah, let me first say problem 4 was the one about which John Conway and I actually wrote a short paper which appeared in Combinatorics, and a filler will appear in February or January next year in the American Mathematical Monthly about this problem. So, and problem 5 is the hardest, and in Zvezda's section 9 I will show you 3 different proofs of it. But you're welcome to start working. You have till tomorrow afternoon. Now, publications. The main goal of my publications is to it will die. Oh, okay. I don't need it anymore. Okay, so the main goal of my publications is affirmative action, if you will. I'm fighting discrimination. Discrimination of young people based on their young age, where, as Dmitri said, we feed them puzzles, and I believe that we should feed them real mathematics. In passing, let me say that I don't believe that mathematics can be taught. I think it's an absurd idea. What a mathematics teacher can do is to create an environment in which students learn mathematics by doing it. Perhaps with a gentle guidance, but that's at the most. And I didn't know what mathematics was, even though I was a winner of, Moscow Olympiads of MGU and Fistech, which is analog to MIT. And I couldn't get research problems in my hands. When I grabbed one at the start of my 3rd undergraduate year, my supervisor, I had a supervisor, like a thesis advisor, that I got as a freshman, actually, told me, no, I want you to just broaden your education, never mind doing research. And he looked into my eyes and he told me, I see that I can't stop you, can I? I said, no, you can't. Well, then whatever you do will be counted as a course paper. And that was my first publication. And so I published this journal, Combinatorics, which is dedicated, as it says here, let me read, a journal on open problems of combinatorial and discrete geometry and related areas. And I have an editorial board that used to include Paul Erdős and still includes Ron Graham, Branko Grünbaum, Peter Johnson, Heiko Harberth from Germany, Jaroslav Neshetril from Czech Republic, János Pach from Hungarian Republic and New York City Republic, and me. And here we publish problem-posing essays that give a motivation why this problem is interesting, what its history, partial results, and literature, so that a young person can take a problem of his or her liking and run with it. And it's 14 years old. reviewed by Mathematical Reviews and Central Blood für Mathematik. And we published actually research results of high school students and undergraduate and graduate students, and a doctoral dissertation of Paul O'Donnell at Rutgers grew up from his contributions to this journal. And I publish books. Let me quickly say that this is Mathematics as Problem Solving. I didn't really write it. I was asked by school district and by a summer program for gifted students to give a course on problem solving. And that's in a sense notes. First time in my life I took notes for teaching. It was published in French too, but I don't particularly like this book because it's no point. The point appears in other books, where my goal was to give the reader a live piece of mathematics, to show interplay of various parts of mathematics and how one solved problems leads to another, and demonstrate a train of mathematical thought. So this was a book that was growing up for 20 years. As an undergraduate, I told Isaac Moiseyevich Yaglom, the famous Russian geometer, that no, I don't want you to publish my article. I will publish the book. Like yours, How Does One Cut a Square? Mine will be How Does One Cut a Triangle? With epigraph, How Does One Cut a Square? Yaglom. And I kept my promise 20 years later, in 1990. This book includes lots of open problems, and this gentleman on the left, Paul Erdős, contributed not only joint problems with me, which is chapter 9, but completely his generalizations that he started sending me letters when he got manuscript. So last chapter is his. This book I like, maybe because I lived with these ideas for 20 years. The third came out jointly by another famous Russian geometer, Vladimir Grigorievich Boltyansky, and I. And this is called Geometric Etudes in Combinatorial Mathematics. It was a joint work, and I think there are good problems there, but two people with decent sense of humor, Boltyansky and I, kept it in check, and it taught me and him a lesson that joint efforts have a tax associated with them. You can't just joke on behalf of two. The next book is Colorado Mathematical Olympiad, the first 10 years and further explorations. Let me say a couple of words about it. Of course, yes, it presents the history of creating a mathematical Olympiad in a city and state where it didn't exist. And that's important as experience for those who want to organize those. And yes, it includes problems, and they're fun, and there are solutions, sometimes 2 or 3 solutions if known. But I delayed writing it. I didn't want to write it because I thought, okay, there will be another book. Colorado Math Olympiads. There are Chinese Math Olympiads, Soviet Math Olympiads, American, international, Slovenian, Polish, Austrian, Iberian, and now it will be Colorado. What's so fun about it? Didn't want to write. And then an idea came to me, inspired by what Kolmogorov once wrote. He wrote that the difference between a problem of mathematical Olympiad and research problem of mathematics is simply that it may take 5 hours to solve an Olympiad problem, and it may take 5,000 hours to solve a research problem. And that idea that actually there is no boundary between good Olympiad problems and research problems inspired me to write second part of this book, Further Explorations, where I take a problem or two from this Olympiad and show that it actually inspires further explorations and unsolved problems. Forefront of mathematics is reachable in one step from competition to research. Then I wrote it in 3 weeks because it was fun writing it. Now, next 4 books that are in various stages, so that you will know what to expect from me next. I am writing a book that will be called Mathematics of Coloring and the Colorful Life of Its Creators. That would be a book on Ramsey theory, on coloring of normal objects like a plane or space, but also coloring integers or real numbers. Early Ramsey theory especially. But I realized that I don't want to just write about mathematics. I want also to write about those people who created that mathematics. And it led me to writing about Frank Ramsey and Isai Schur and perhaps Hillel Furstenberg, yes. But also about Bartel Lindert van der Waarden. You know van der Waarden, Modern Algebra. Who doesn't know that book? But I opened undergraduate algebraic geometry in 1988, University of Cambridge Press. And it said that van der Waarden was perceived as a Nazi collaborator. Just imagine, black and white, in a very respectable Cambridge publisher. And yet everyone who knew him wrote that he was a man of utmost integrity. At any rate, there is no truth in anything that has been written about van der Waarden, and that research I published in Combinatorics in 3 parts. Third part is coming out in January. And Janos Pach, at any rate, there is no time for that. The one after that will be Open Problems of PGOM Erdős, Poor Great Old Man Erdős. That book that for years Paul Erdős and I were working on together, and now I will have to finish it all by myself. Then second volume of Colorado Math Olympiad, because second 20 years are over, so I must write. And after that, the book on art on frontier among the tribal cultures of West Equatorial Africa, Gabon. So that's the plan. Thank you.